Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 12. Hello there. The volume formula of a sphere. A sphere. Classwork opening exercise. Picture a marble and a beach ball. Okay, so here's a marble. Picture a marble and a beach ball. There they are. Which one would you describe as a sphere? What differences between the two could possibly impact how we describe what a sphere is? Okay, so I'm just going to leave that to an open-ended question, but we're going to go on now and define these. So, definition of a sphere. A sphere is given a point C in the three-dimensional space and a number r, radius greater than 0. The sphere with center C and radius r is a set of all points in space that are the distance r from that point C. Every direction, left, right, up, down, and every diagonal. That is the definition of a sphere. Continuing though, solid sphere or a ball, given a point C in the three-dimensional space and a number r greater than 0, the solid sphere or ball with center C and radius r is a set of all points in space whose distance from the point C is less than or equal to r. So I could pick a point equal to r, and that would be the shell, if you will. So if I just use r greater than 0 and all points equal distance from the center C to r, it would be this ball with nothing but the outer shell, that distance from C. But if I take this marble, it's all those points distance from C and including those distances that are less than and filling in the interior. So that is a really good definition. Okay, so under characteristics, we want to say that a sphere is hollow and a solid sphere is filled or solid. Okay, so can you come up with examples? What would you think of when you're talking about this? Well, give you a minute, see if you can come up with some, pause the video, see if you can fill that in, and we'll see if our answers match. They could be different, they could be the same and still be correct. There are many different examples. So if we're talking about a sphere, we could have a beach ball, which I have up here on the screen, or a soap bubble, if you're blowing bubbles. A solid sphere could be a marble, a planet, and many other things that are solid. A golf ball, any kind of ball. A tennis ball would be a sphere that's hollow, and so on. Baseball would be solid. So non-examples. Okay, so non-examples, we can get really ridiculous. A non-example could be a spherical shape, like an egg-shaped figure. That is not a sphere. An egg-shaped figure is not a sphere. And for a solid sphere, a circle, definitely not solid, and it's not a sphere. So there's all kinds of non-examples. You could say a taco cat is not a sphere or a solid sphere. Anyhow. So down here we have some diagrams. We have a plane, and we have another plane, distance h, up to here. And the distance from the bottom to the top r is the same for all three figures. Okay. This is a hemisphere. Hemi meaning half. So hemisphere is half a sphere. So if we're talking about the Earth and we start at the equator and just go north of the equator, everything north of the equator is a hemisphere. It's the northern hemisphere. And the southern hemisphere would be anything south of the equator. This is a cone T, and this is a cylinder S. So if you take and cut this out it has a radius. If you come up here, as h increases, the radius is decreasing. It's getting shorter and shorter. As the height increases, the radius decreases. If we have a cone like so, the radius down here is 0. It's just a point. But as h increases, the radius is increasing until it maxes out at the top. And a cylinder, the radius is r. Doesn't matter how high we go, the radius is still r. And at the top, still r. So the cylinder here is an example of, this one's Cavalieri's principle. No matter where you slice it, if the slice is horizontal to the base, the slices are congruent or similar, not similar, congruent to the base, same area, and therefore the volume can be determined by multiple areas. Okay, so we need to delve into this a little deeper to find the volume of these things. So I have started marking this up. So we have a circle here. It looks like an ellipse, but it is a circle because we're looking at it from an angle. It is smaller than the base area circle because as height increases, the radius of that section gets smaller and smaller. I also drew a blue line from the point where the height center, the center of the cylinder, or the center of the sphere, hemisphere is, up to a point at the level we are at. So if this distance from here to here is r, keep in mind what the formula of a sphere is. And a solid sphere is, or a sphere is distance r from the point C. Every point r from the point, or let me rephrase that. The center C with a radius of r. Radius of r means every point is the same distance from the center to the surface of the sphere or hemisphere in this case. So this point out to here is called capital R. That is a radius. Well, if I drew a blue line from here to here, it's touching the edge, it's going to the center. That is also length R. These two line segments are equal. And if you see, we have now created a right triangle. So I can find the area of D1 in terms of D1. I could say, whoops, I could say the area of D1 equals pi r sub 1, which is my radius of that smaller one, squared. That's a 1 there, not a comma. So area of D sub 1 is pi r sub 1 squared. How can we find r sub 1 in terms of h, the height, and capital R? Well, if you now focus on that right triangle, and let me bring it in. Okay, so now we have a right triangle here. So what can I do? Well, I can say a squared plus b squared equals c squared, the Pythagorean theorem. Well, in this case, I can call a r sub 1 squared plus b, which is my h squared, equals my hypotenuse r squared. So getting r sub 1 by itself would be r sub 1 squared equals r squared minus h squared, subtracting h squared from both sides. But then I can take the square root of r sub 1 squared, and that would give me r sub 1 equals the square root of r squared minus the height squared. Okay, so why did I do this? Well, you see this r sub 1 right here? You see this r sub 1 right here? This is going to substitute in here. So now I'm going to say the area of d sub 1 equals pi, my r is here, which is the square root of r squared minus h squared, and we're going to square that. because it's r sub 1 squared. So the area of d sub 1 is going to equal, and when I square the square root, it's going to go away, and we can distribute the pi. But first, let's just get rid of the pi, and then in parentheses, we're just going to have r squared minus h squared, because the squared will cancel the square root. And then I can distribute my pi, forgot my parenthesis there. So a area of d sub 1 equals pi capital R squared minus the height. I'm sorry, minus pi times the height squared. We're doing the distributive property. Pi height squared. Okay, so I just cleaned this up a little bit and made a nice neat column. Our answer is right here. The area of D1, which is right here, is pi r squared minus pi h squared. Okay, so we're going to do the same now with this cylinder. One thing you need to keep in mind is that the radius is r right here. And notice this height right here is r. So from here all the way to here, so let's draw that. Let's do it in red. The distance from here up to here is also r. So I will label that as r. That is also a height of r. So remember what we're doing here. We're going to, here's the cross section, by the way, cut out. So you can see that this is r and this is r. R sub 2 is right here and h is from here to here only. So let me draw a red line right there to remind you that h is not the entire height. H is from here to there. Okay, so let's use green this time. What are we going to find? Well, we have to use similar triangles, and we can take r sub 2 is to h. So we can write r sub 2, the radius 2, the smaller cylinder, the smaller circle, radius of 2 is to the height h. So what I'm talking about is this side is to this side as this side is to this side. That's interesting. That equals 1. Because anything divided by itself is 1. So if r2 is 5, then this distance is 5. So h equals r sub 2. Okay. Now let's do the area of D2. So let me move this down below because that's what I was working out. The other stuff was underneath. I want everything to line up nicely. So now we're going to go up here. I want to find the area of D2. So the area of D sub 2 equals, remember, area of a circle is pi r sub 2 squared times height h. So we are just talking about this and this. We're finding the area of this circle right here. So the area of D sub 2 equals pi r squared sub 2, pi r sub 2 squared times height, which equals, now remember, r sub 2 over h is 1. Okay, made a slight mistake there. I don't want h. I'm looking for area of a circle, not the volume of that cylinder cone. Okay, area of D sub 2 is pi r squared, pi r sub 2 squared, period, the end. But pi r sub 2 is equal to h. Okay, did you hear what I said? R sub 2 equals h, because anything divided by itself is 1. Since this was equal to r over r, that's a ratio of 1 to 1. So the radius is equal to the height here. So if I just called that h, r sub squared, I can substitute in the height instead of the r sub 2, and I can say it's pi h. So the area of this circle is pi times the height squared, because r sub 2 was squared. So r sub 2 equals h. Therefore, pi r sub 2 squared is pi h sub 2, or pi h squared. Okay, so what are we going to do now? Well, let's think about this. We found the area of this. We just found the area of this, didn't we? It's pi h squared. So I would assume that we would, find the area of this. Okay? So we're finding the areas all on this level that is h above the floor or base. So now I want to find the area of d sub 3. And it is a circle. An area of a circle is pi r squared. But in this case, our r is called r sub 3. So that one was easy. Area of D3 equals pi r sub 3 squared, but it's equal. R sub 3 is equal to r, so I can say the area of D sub 3 equals pi capital R squared, because r sub 3 equals capital R. Cylinders do not change in radius. Okay, we're finally leading up to the results of this lengthy explanation, but if you follow through with this, this is really cool. Look what just happened. So we took Cavalieri's property principle, and we went up a certain level parallel to the floor or base, a distance h, and this radius shrunk, this radius got larger, this radius stayed the same. So if we take a hemisphere and a cone and a cylinder and find the areas of the circles at this height, look what it ended up being. The area of d sub 1 was pi r squared minus pi h squared. The area of d sub 2 was pi h squared, and the area of d3 was pi r squared. Again, look at this, pi r squared minus h squared, and this is h squared. So this is this minus this, or this plus this equals this. Mind equals blown. So the area of d sub 1 plus the area of d sub 2 equals the area of d sub 3. This plus this would cancel the pi h squareds. Minus pi h squared plus pi h squared goes away, and we just get pi r squared. All right? So the area of D1 plus the area of D2 equals the area of D3. And if I just wrote these instead, it would be pi r squared minus pi h squared plus pi h squared equals pi r squared. Notice the minus pi h squared plus pi h squared would cancel, and pi r squared equals pi r squared. Okay? Okay, so if you're wondering why we did this, here's what I'm going to do now. Now we're going to discuss their volumes. What is the volume of a cylinder? We know that. The volume of a cylinder, which is volume of this here, S, is, and I'm going to try to keep these in the same order. The volume of, I'll use a subscript. The volume of cylinder S, so the volume of S equals pi r squared times height. Agreed? We all know that. The volume of a cone we already know cone T is 1/3 pi r squared. Okay. So if we are saying the area of this plus the area of this equals the area of this, then the volume of this, and what would we know about this and this? How can we bring this into volume? Okay, I want to fix this. I made a mistake, by the way, with that squared, but I want to fix how I'm wording this. So let's just go vertically. The volume of S equals, okay, volume of cylinder S is pi r squared. The volume of cone T equals 1/3 pi r squared. Okay, I did it again. Volume is cubed. 1/3 pi r cubed. And this is pi r cubed. I don't know why I keep saying squared. It's volume. Volume is pi r cubed. And this is 1/3 pi r cubed. This is area up here. Now we're talking volume. The volume of this cylinder is pi r squared times height, but h equals r. Okay, when we said that over here. Okay, I wasn't being very clear here, so let's look at this. Volume of S, the cylinder, is base area times height. It would be pi r squared times h, but h is equal to capital R, so I can substitute it. Pi r squared times h. R squared h is the same as r squared. H equals r, so that'd be r cubed. That's why that is pi r cubed. The volume of T, which is the cone, is 1/3 pi r squared times height, but the h is r, so that's r cubed. Okay, that's why I kept writing squared, because I'm thinking with that h, the formula is pi r squared times height. H becomes r, giving us a power of 3 in r. Okay, so now we're going to do the volume of the hemisphere H. Okay, the volume of the hemisphere H plus 1/3 pi r cubed equals pi r cubed, right? Because we're looking at this. If the area of this plus the area of this, if the area of the hemisphere plus the area of the cone equals the area of the cylinder, then the volume of, by Cavalieri's principle, the volume of this sphere plus the volume of this cone will equal the volume of the cylinder. So the volume of H plus this equals this. So now I can find the volume of H by subtracting 1/3 pi r cubed from both sides, and I get the volume of H equals 2/3 pi r cubed. Okay, now keep in mind that is a hemisphere. So if we have two hemispheres, we form a sphere. So the volume of a sphere, I'll use the word because we already used S for the cylinder here. The volume of a sphere equals 2 hemispheres. Okay? So the volume of a sphere equals 2 times this, which is 4/3 pi r cubed. There is the volume of a sphere. Okay, page 2 brings us to an example. It says, use your knowledge about the volumes of cones and cylinders to find the volume of a solid hemisphere of radius capital R. Well, if we just look back at our last page, The volume of a sphere is 4/3 pi capital R cubed, and there it is. So V equals 4/3 pi R cubed. Okay, so there is the formula we are going to use. Exercise, find the volume of a sphere. Find the volume of a sphere. So the first thing I do is write the formula. V equals 4/3 pi R cubed. With a diameter of 12 centimeters. If the diameter is 12, then the radius is half of that. So there's my given. So I substitute in the given. Volume equals 4/3 pi 6 cubed. 6 cubed is 216. So the volume of is 4/3 pi 216. 6, 7, 8, 9. If 3 will go into the sum of these, 3 will go into it. 3 goes into 9, so I can reduce this. 4 pi. 3 goes into 21 7 times. 3 goes into 6 twice. And 4 times 72. 4 times 2 is 8. 7 times 4 is 28. I get 288 pi centimeters cubed. Use your unit of measure. So the volume is 288 pi centimeters cubed. Okay, if we wanted to do an approximation, then we would say 288 pi, and we'd get approximately 904.78. Cubic centimeters. Page 3, exercise 2 and 3. Pause the video, see if you can do these, and here we go. All right, so we have an ice cream cone, 11 centimeters deep and 5 centimeters across the opening of the cone. It is a cone. So I will draw a cone for starters. I would like to draw a diagram of this. So here is the cone, and if I come down here, there's my ice cream cone right there. The ice cream cone is 11 centimeters deep. So from here down to here is 11 centimeters. And 5 centimeters across the opening of the cone. So from here to here is my radius, would be 2.5 cm. Okay, 5 centimeters is the diameter. 2 hemisphere-shaped scoops of ice cream, which also have diameters of 5 centimeters, are placed on top of the cone. 2 hemispheres constitute a sphere. So we have a sphere of ice cream on the cone. If the ice cream were to melt into the cone, would it overflow? Okay, so what they're saying is that we have a hemisphere and another hemisphere rotated 180 degrees. So this is our cone here, and this is our ice cream here. What they're saying is the ice cream is sitting on top right there, and they want to know that if it melts, will the cone catch it all, or will it overflow? So I want to find the volume of the ice cream and the volume of the cone. If the ice cream's volume is more than the cone, we have an overflow. If the cone has a volume more than the ice cream, it will catch it all. Got it? That's what we're doing. So we want to find the volume of both. This is also 5 centimeters. So if I put a dot here, this radius here is 2.5 centimeters. Okay, so let's find the volume of the ice cream first. Volume of the ice cream, volume I, equals 4/3 pi R cubed. So the volume of the ice cream equals 4/3 pi 2.5 cubed. While I'm doing that, I'm going to do the volume of the cone, which is 1/3 pi r squared times height. So the volume of the cone is 1/3 pi 2.5 squared times the height 11. So which is more? That's what we're trying to find out. So let's continue over here. Volume of ice cream is 4/3 pi. I need 2.5 squared. It's 6.25, I believe. 2.5, I'm sorry, cubed. Try that again. Math 3. 2.5 cubed is 15.625. Okay, so this is 15.625. So I'm going to multiply that by 4/3. And I get 20.83 approximately. So the volume of the ice cream is approximately 20.83 pi, and it's cubic centimeters. We can leave it in terms of pi and just look at the numbers when we're done. So the volume of the cone is going to be 1/3 pi 6.25 times 11. So that was 2.5 squared, enter, times 11 times 11. And we get 68.75. So the volume of the cone is 68.75 pi centimeters cubed. Okay, I did forget one thing. I forgot my 1/3. So let's fix that. I did this divided by 3 would give me 22.91. So let me fix this. This is 22.91 pi centimeters cubed. That makes more sense. Okay, so the cone is a little bit bigger. 22 is a little bit more than 20. You could have done this a different way, but this is an approximation. Didn't close my parentheses here. Doesn't matter. So anyway, the volume of the cone is greater than the volume of the ice cream. So the answer is no. It will not overflow. Okay, number 3. Bouncy rubber balls are composed of hollow rubber shells 0.4 inches thick and an outside diameter of 1.2 inches. The price of rubber needed to produce this toy is 3.5 cents per cubic inch. What is the cost of producing one case which holds 50 balls, round to the nearest penny? Okay, so the outer shell of the ball's 0.4 inches thick. So the hollow center has a diameter of 1.2 minus 0.4 is 0.8. Okay, so the hollow center is a diameter of 0.8 inches. So from the center to the inside edge of the ball is 0.8. You go through the thickness of the ball 0.4 and the outer diameter is 1.2. Got it? Good. All right. So the radius is, so this is diameter inside. So the radius is half of that, which is 0.4 inches for starters. Okay. So the volume of a sphere is 4/3 pi r cubed. Okay, now we got to keep in mind that the outside diameter is 1.2. So the outside radius equals 0.6 inches. Okay. So we need to know how much rubber is used to make a ball. So if you take the outside diameter or the volume of the outside, that would be a solid ball. If we subtract the volume of the inside from the volume of the outside, it will give us the volume of the rubber used to make the ball. So the volume outside is 4/3 pi r cubed. So let me rewrite this before I start. The volume of rubber equals volume of the outside minus the volume of the inside. Does that make sense? So the volume of the rubber is going to be the volume of the outside, which is 4/3 pi r cubed, minus the volume of the inside, which is 4/3 pi, and this would be radius outside, radius inside cubed. So we substitute in our givens. So the volume of the rubber equals 4/3. Okay, pi. Outside radius is 0.6 squared. No, it's cubed. Why do I have a squared there? Cubed. 4/3 pi r cubed. Minus 4/3 pi, radius interior is 0.4 cubed. Okay, so the volume of the rubber will be 4/3 pi and 0.6 cubed. What is this doing? 0.6 cubed is 0.216. Okay. And actually what I can do here is I can factor out a 4/3 pi. And then I would just have this 0.216 minus 0.4 cubed. Zero 0.064. Okay, so the volume of the rubber would equal 4/3 pi, and 0.216 minus 0.064 equals 0.152. Okay, and then we just put that in the calculator, including the pi. So 4 divided by 3 pi times 0.152 equals 0.6367, 0.6367, and it's inches cubed. Okay, so now we can find the total cost. It says, what's the total cost of purchasing a case of rubber balls, which has 50 in it? So total cost equals the price of the ball, rubber, which is 0.035. Okay. Price of the rubber times the amount of rubber in one ball times number of balls in a case, 50. Okay, so our total cost is going to be this amount, and I'm going to use this in my calculator because it's not rounded, and I'm going to multiply that by 0.035 times 50. And that is going to give me 1 point, is that right? Yeah, about $1.11. So the total cost is approximately $1.11. Okay, so now part B says, if each ball is sold for 10 cents, how much profit is earned on each ball sold? So that would be total sales. Total sales equals selling price times the number of units sold. So the total sales is going to equal the selling price, and the selling price is 10 cents. If each ball is sold for 10 cents, 0.10, units sold 50, then the total sales are 50 times 10 cents or $5. Then it says how much profit is earned on each ball sold. Okay, so let's change colors for this. So profit equals sales minus expenses. Okay, so our total sales were $5 minus our expenses, which is this here. That's the cost of making them, which is $1.11. Then the profit would be 5 minus $1.11, which would be $3.89. That's total profit. How much profit is earned on each ball sold. So then we take that $3.89. So profit per unit, can't write, profit per unit is profit per 50 units. So you take 389 divided by 50. So 3.89 divided by 50 equals 0.0778. So it's approximately 0.0778, or about approximately 8 cents. Okay. Actually, that wouldn't be 0.8 cents. That's not correct. Let me just put a dollar sign in front. $0.08 is 8 cents. So about 8 cents profit per ball. Okay, page 4 brings us to an extension. You might have done this in class, you might not. It's an extension. All right, so we have this sphere, and we want to find the surface area of it. So picture all these regions. Okay, so this would be like coming to a point in the center. So all these distances by definition would be R. Actually, I'm using different colors. Green's hard to see on that color. Let's use red. So this distance from here to the center is R. That's R. This is R. This is R. This is R. By definition of a sphere, it is the set of all points R radius away from the center C. So we have these areas here. So if we wanted to find the surface area of a sphere, we can say that the volume of the sphere, well, let's see, how are we going to do this? We can do the volume of each piece. So the volume of this little piece here that we call A sub 1, the volume of A1 equals, it is very close. Let's just say it's an approximately a circle here. but it wouldn't be a circle because we'd have these little pieces that would be not counted. So, but we're going to do an approximation. So if this is a circle and it goes to a point, that is a cone. So the volume of a cone is 1/3 pi r cubed. No, it's not. Just kidding. 1/3 pi r squared times the height, which is capital R. Okay. And if we call the base just simply A1, then the volume of A sub 1 would equal 1/3 A sub 1, the base area, pi r squared. That's what we're calling A sub 1. The volume of A sub 1 is 1/3 A sub 1 times R. So now how is the volume of the sphere related to the volume of the cone? Well, the volume of the sphere we know is, volume of the sphere is, let's just do that. Volume of sphere is 4/3 pi r cubed. And let's use a capital R. So that's going to be our radius of the sphere. So the volume of the sphere is 4/3 pi r cubed. This little r would be a radius of one of the cylinders, if you will. Got it? All right. Just might be a little tough to get your head around, but the volume of this sphere is 4/3 pi r cubed. So if we take that 4/3 pi r cubed, we can say it is approximately equal to the sum, 1/3 times the sum of A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 plus ... A sub n, all the way out to the last one, depending on how many we use, times R. Okay? Okay, so, but then we now can say, well, what would these all be? Well, if those are all the bases and they all cover the whole thing, then those could be our surface area. And we'll call it S. So look what's going to happen. We're going to take the volume, and it's going to be approximately 1/3 the surface area times R. Okay, that makes sense? So 4/3 pi r cubed is approximately 1/3 surface area times that R. So if I want to solve for S now, multiply both sides by 3. Let's do this in blue. So if I multiply this by 3/1 and multiply this by 3/1, the 3 and the 1/3 cancel. These 3 cancel, and I get a 4. Pi r cubed equals, let's use an equal sign now, S times R. So if I want to know what R is, I divide by R, divide by R. These cancel, and I get S equals R cubed divided by R to the 1 is R squared. And we have 4 pi R squared. So that, my friends, is the surface area of a sphere. Okay? Right there. Surface area of a sphere is 4 pi r squared. That was kind of neat. Okay, page 5 brings us to the end of lesson 12. That was a really cool lesson. I enjoyed that. Lesson summary, review the lesson summary on sphere and solid sphere or ball, and go do your problem set.